we're going to talk about a one sample t-test for population mean. So just like before with confidence intervals, we use a z-test if we know our population standard deviation. We know a t-test if we know our sample standard deviation. So let's make a note of that because that's usually one of the most repeated questions. So we use a z-test if you know population standard deviation. Use a t-test if you know the sample standard deviation. So to use our test, we use this test when we're interested in the value of our population mean mu, and we don't know our population standard deviation. So instead we have to estimate it with our sample standard deviation, and that's why we switch from z to t. So conditions to do this test is your population has to be normally distributed or your sample size has to be large, of at least 30. Our null hypothesis will always be that our mean is equal to some number. And our test statistic is very similar to our t-test, of we're going to do x bar minus our hypothesized mean over our sample standard deviation s over square root of n. Now, if you remember from before, t distributions, when we did our confidence intervals, have degrees of freedom, and the degrees of freedom are still n minus 1. So let's look at what that would make our p-values. Remember, our p-value is just always the area in the tail, or tails as the case may be. So if you have something where it's like, say, mu is greater than 3, let's say it's 3, okay, then you would find your test statistic and find the area to the right because it's greater than. If you have something like mu is less than 3, then you would find your test statistic and find the area in the left tail. Just whatever your test statistic t is. And if you had something like mu is not equal to 3, then you would find your test statistic, which might either be positive or negative, and then you find the area in both tails. Or if you want, find the area in one tail and times it by 2, which is why we have the 2 here. So if you have a greater than, it's right tail, less than is left tail, not equal to is both tails. Now we're actually going to do this calculate test in our calculator now instead of doing it by hand. So you'll just be looking for your test options. You want a t-test, which in TI Casio is t-test. Casio is just t. And then you have to do 1s for one sample. Okay. So let's try it. A bank wants to know if their mean debt to equity ratio is less than 1.5. They want to make sure they don't commit a type 1 error, so they make alpha equal to 0.01. So they made a small alpha. They found, because remember alpha is our chance of making a type 1 error, so if they make alpha 1.01, that means they only have a 1% chance of making a type 1 error. So they found a sample of 15 of their commercial loan accounts. So that tells me n equals 15. Here's all of the values there. And because it told me n equals 15, that's a small sample, I need to check if it's normal. So I look here, my box plot is pretty symmetric, just maybe one kind of possible outlier. See the dashed lines, if it's in between there, it's just kind of a possible outlier. My distribution looks fairly normal, really. And if you remember, this is a very small sample size. Small sample sizes never look quite as good, okay? But I think that actually looks very normal. That's fairly close to a straight line. I would say this one looks normal enough. So our conditions are met. Let's go through everything else in our hypothesis test. We need to write down alpha. They told me alpha equals 0.01. Notice here I gave you the summary statistics from our computer. And let's write down everything they told me. So count, well that's n equals 15. We already knew that. My mean, so that would be x bar equals 1.3433. My sample variance is 0.0369, and my sample standard deviation, so variance is s squared equals 0.0369. My sample standard deviation, s, equals 0.1921. Okay. If you ever want to know how to do this actually by hand instead of with your calculator, you can go look for my videos that I made for Stats 3000, and they do these exact same problems but by hand. So we pull up our calculator. We're looking for a one sample t-test. And the hardest thing I need to figure out is what tail I should be interested in and my hypotheses. So we want to know if our mean debt to equity ratio is less than 1.5. So when I set up my hypotheses, because calculators can't do that for you, the null hypothesis would be that my mean equals 1.5. You'll notice that the null is always an equal sign. My alternative, I'm interested in knowing if my mean is less than 1.5. So again, the null is always going to be an equals to, and the alternative is kind of what you're hoping to prove. And we're kind of hoping to show that our mean is less than 1.5. So those are our hypotheses. Now we'll use our calculator to find our test statistic. Let's see, so if I remember, I think is under stats. We want to go to tests, and we need a t-test. So just here, notice there's a z-test, which we learned how to do by hand. There's a t-test, and then there's some other things, but we just want a basic t-test. You can choose between putting in the raw data or the summary statistics. We'll just kind of always do summary statistics to save time. Our hypothesized mean is 1.5. That's the mu naught. Our x bar is 1.3433. Sx, when they say Sx, that means your S, your standard deviation. So Sx is 0.1921. And N is 15. Then notice here it gives you your comparison. It lets me do a not equal to, it lets me do a less, or it lets me do a greater than. We chose we wanted to do a less, so let's select that. And then looks like I can choose between calculate or draw. Let's see what happens if I do draw. Notice it drew my curve for me. It did my t-test. It says t equals, my test statistic, t equals negative 3.1593. Now, because we said this was a less than, if my test statistic is negative 3.1593, I would want to shade to the left. You can't quite see it on here unless you zoom in, but notice they shaded. The blue's a little bit darker right here from negative 3 on. And it tells me that that area, P, equals 0.0035. So it told me my test statistic, and now it tells me my p-value equals 0.0035. I kind of like the draw just because that helps reinforce the basic concepts. But you could also just choose calculate. So all of my stuff is the same. Let's calculate. And so if I just use calculate, notice it tells me all these things. It tells me my mean that I tested was mean is less than 1.5. It tells me my t-test statistic is negative 3.15. We knew that. And our p-value is 0.00348. And it also repeated your summary information for you. So you can use calculate or draw. Again, draw is nice because it reinforces the idea that this area p-value is just the area in the tail. Now is the part where you come in again, because calculators won't do this part for you. You say my p-value, which equals 0.0035, is link compared to alpha. So how does that compare to alpha equals 0.01? So 0.0035 is smaller than alpha. So my p-value is small. Anytime you have a small p-value, you reject your null hypothesis. Okay, and that means then that you'll have evidence for the alternative hypothesis. So now let's interpret it. We say something like, we have very strong evidence, and I'm saying very strong because it's smaller than alpha equals 0.01. Very strong evidence that the mean debt to equity ratio for all the accounts, because we only took a sample of 15, and from our sample of 15, our sample mean was less than 1.5. But now we're saying we have very strong evidence that the mean for all of the accounts is less than 1.5. And finally, let's interpret the p-value, because this is probably the most important thing, one of the most important things you can walk out of this class knowing, is how to interpret the p-value. So our p-value always tells us it's the probability of getting our sample data, or something more extreme, if the null is true. And you can kind of change the order you put it in, but those three things all have to be there. So I would say something like, we only have a 0.0035 chance of getting our sample mean of, let's see, our sample mean was 1.3433, or something smaller, because smaller values were more evidence that mu is less than 1.5, or something smaller, if our population mean really is 1.5. So we're saying we only had a 0.0035% chance of getting our sample mean of 1.3433, or something smaller, if our population mean really is 1.5. So that's what our p-value tells us. Now, because we did get a sample mean of 1.3433, and there was such a small chance of getting that if our mean really was 1.5, I now believe that the population mean really wasn't 1.5. In fact, I believe it was less than it. So I believe the mean was less than 1.5. So that is a t-test. Putting it in your calculator saves you a little bit of time. Not too much actually, because most of what we do actually has to kind of be thought out by a human. It's much more logical, but it will save you some time on the computations. So there's a problem for you to try. Okay. I want to make sure you remember to read all of these notes, even on the Now You Try problems. So when you go through and you want to decide if you should have like a one-sided or two-sided alternative, that means, did you want mu is less than 3, mu is greater than 3, mu is not equal to 3? You have to decide those. You're supposed to decide those before you look at the data. That's supposed to be based on your theory, okay, of your actual practical theory for this, of like, oh, should doing this process increase a rate of return, or should doing this process make it less than what it was before? That's supposed to be based on the theory. You're not supposed to decide that based on the data. If your data suggests that maybe you should have picked a different alternative hypothesis, you're usually, theoretically, supposed to do that again with a new data sample. Okay. When you look at the data first, we call that data snooping, and that's kind of unethical in the statistics world. So let's try this example. I want to see if the mean of the heights of everyone on campus is different from 5, 10, or 70 inches. Notice it just says different than. It doesn't actually say we think it's higher or lower. I took a sample of 25 imaginary people. Here are their heights. Okay. We want to conduct this hypothesis test with alpha equals 0.05. I notice here I gave you a lot of summary information from my computer. Okay. I have written out a lot of steps here. Let's go through them step by step. So alpha equals 0.05. We need to check our conditions, which is that n is at least 30, or our sample data looks normal. Okay. Well, in our case, we only have n equals 25. That is small, so we don't have greater than or equal to 30. But if you look at my normal curve plot, that looks very much like a straight line. I think it looks normal enough. Then you do your hypotheses. My null hypothesis will always be an equals. And then the alternative is what you have to think of. So they said different than 5, 10, or 70 inches. So my null, the boring thing, would be that it is 70 inches. What I'm hoping to show is that it's different from 70 inches, or not equal to 70 inches. Now, if you do it with the computer output, I actually want you to, at this point, go through and write down what are your sample size, mean, and standard deviation. So if you were actually writing up a research paper, you would tell people in advance, these are, like, this is the alpha I'm going to use, these are the hypotheses I'm going to use. Then you tell them your sample information like this, you ask if the conditions are met, and then you actually do the test. So let's see, sample size, n equals 25. So you can see here, n equals 25. My test statistic, that would be t. Oh, sorry, I'm getting ahead of myself. Sample size, mean, and standard deviation. So my mean, the mean of the heights, is 67.16. So x bar equals 67.16. The standard deviation, notice there's here standard deviation, standard error. The standard deviation is actually S. So 4.327. The standard error, if you remember, is S over square root of n. We actually just want S. Okay. And, okay, so we did that. Now come up and look, oh, here's t. My test statistic, t equals negative 3.28. Computers will usually tell you degrees of freedom. So my degrees of freedom is 24. For some reason our calculators don't, but the computers will. Our p-value, notice here, p-value equals 0.0031. Now here's where you need to think a little bit. Okay. So look at your alternative. Mu is not equal to 70. If it's a not equal to, you know you want the area in both tails. So you take your test statistic of negative 3.28, this would then be positive 3.28, and you find the area in both tails. Because it's a not equal to, that's area in both tails. The reason you need to think about that is say, okay, that's supposed to be two tails. Check and see right here. It did tell me p-value equals two-tailed. Sometimes it might give you a tail that you weren't anticipating, or you might have to think about it or do some computations to get what you want. But it did say two-tailed. We want a two-tailed. We're good with our p-value. And then we go through and interpret our results. So our p-value of 0.0031. So p-value 0.0031 is blank compared to alpha equals 0.05. So that would still be smaller. Okay. So we will reject our null hypothesis. So if we reject our null hypothesis, we have evidence for the alternative. So here's my alternative, mu equals 70. So we have evidence that the population mean height is different from 70 inches. Now, if you're like me, you might say, it's not as interesting to do a two-sided alternative because all we said now is just that it's different from 70 inches. We didn't actually say whether it's less than 70 or greater than 70. We just said different from 70. Now, to continue this example, I found a 95% confidence interval for our population mean height to be 65.37 to 68.95. And so if I found that confidence interval, then I could say I'm 95% confident that my population mean mu is between 65 and 68 inches. So if you are 95% confident that our population mean is between 65 and 68, would you be inclined to believe that my mean is 70? Well, is 70 inside that confidence interval? So 70 is not between 65.37 and 68.95. So just based on the confidence interval, I would think that mu is not equal to 70 because 70 is not in that confidence interval. So another way you could conduct a hypothesis test is just to see if your null hypothesis of 70 is inside your confidence interval. Because if 70 is not inside your confidence interval, then you would think that 70 is not going to be a plausible value for mu, and you would think that mu is then not equal to 70. So that's another way you can do a hypothesis test. We won't really focus on it in this class, but it is interesting to note. In this example, your boss wants you to run a hypothesis test to see if the mean is less than 87 for a data set with a sample size of 20. So if n equals 20, that's a small sample. Okay, and when I look at this normal curve plot, that is definitely not a straight line. Okay. And so this data is not normal. So if I have a small sample size and my data is not normal, we cannot do a t-test on this data. Okay, it does not meet the conditions. So we would have to use a non-parametric method, which again we don't actually talk about in this class.